Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to welcome Ari Gurfinkel from CMU. And in a fitting tribute to Curiosity landing on Mars, he's going to talk about UFOs and the state space explosion. So take it away.
Okay. Hi, everybody. So this is a joint work with Aus, who's here in big letters, in Ili and Marcia Chechik. He's in big letters because well, he did a lot of the work, and also because he's right over there. So if you have any sort of questions that you think about after I'm gone, he's the one to ask. I give no warranty, so any mistakes I have, you can't sue my employer, or I have to do it. I'm sorry. Okay, so let me start. So what this work is about is sort of automated software analysis. I'm not going to spend a lot of time or any time motivating why this is interesting, just sort of position where this work fits. So from my perspective, an automated analysis is this box. It takes a program, and it tells us whether the program is correct or whether it's incorrect. And there's two major approaches to building this box. One is pioneered by Ed Clark, Alan Emerson, and Joseph Sifakis, which is now called software model checking, or model checking with predicate abstraction and so on. And another way to build this box is through something called abstract interpretation, which was pioneered by Cousseau and Cousseau in about the same time. The reason why I'm showing you this both pictures is sort of my work typically is mostly working in between these two realms, so doing some software model checking applications with abstract interpretation, or some abstract interpretation with software model checking. This particular work sort of fits more here, and the follow-up to it fits more here, if you're interested about it later. I get a question, why is this picture this way? And I just couldn't find a picture of Radia. That's the picture she has on her webpage. And there are no other there are no other pictures if you go to Google Images and look for her. So so here's the outline. So I'll talk about sort of the way we classify approaches to software model checking as over or under approximation-driven. And the keyword here is driven. So both approaches use partial models and things like that, but we sort of separate what's the primary, what's secondary. And I'll talk about UFO, which is our way of combining the two. And in UFO, I'll talk about the exploration strategy and the refinement strategy, which is a two important step there, and then conclude. And I don't know if I have to say this, but this talk will be very informal, so if you have questions, please stop and ask. Don't wait until the end. OK, so here's a picture of something called CEGAR, counterexample guided abstraction refinement. We'll say it's an over-approximation-driven approach, and this is how it works. We start with a program. We start with some abstract domain, so some initial set of predicates, compute an invariant, check whether the invariant is safe. If it is, we're done. If the invariant is not safe, we look for an abstract counterexample, use an SMT solver to check whether it's feasible. If it is, we have a counterexample, we're done. If not, we're going to go and somehow refine our post operator, get more predicates, using either interpolation or weakest precondition, and repeat this process. So we'll say this is an over-approximation-driven approach because a lot of the work is done sort of in this over-approximating part of it. So we do all this work just to get the right abstract domain, and then a lot of the analysis is done in this abstract computation. So I'll give you an example just so that you'll see exactly what I mean. So we have this program on the left-hand side. It has an error location, and we're trying to check whether error is reachable. So the first question, is it reachable or not? Assuming no overflows and underflows, I guess. Well, it seems like it's. Okay, so it's not.
If it overflows or not.
Right. So if there's no overflow, then there is unreachable. And so let's see how will the CEGAR approach work on it. So the first thing we do is we build an initial abstraction where, for example, we'll take no predicate, just the control flow of a program. And it will look something like this, where stars mean a non-deterministic choice. We then build a model out of this thing, which looks something like this. And then we ask whether error, which is node 5, is reachable. Is it reachable here?
Yes. Definitely reachable.
Yeah, it is reachable. We have a counterexample. Now we have to see whether it's a real counterexample. So we're going to our feasibility check. We map this counterexample back to the original program. We say, OK, from 1 to 2, that's OK. From 2 to 4 is a problem. OK, so from 1 to 2, the program actually goes from location 1 to location 2. It doesn't go from location 2 to location 4. And the reason is that we need this predicate. This is what blocks that execution. So we take this predicate, we add it to the list of predicates, build a new abstraction, where now we'll have a Boolean variable b that will represent this predicate. And then everything that can be abstracted by b is abstracted by it as precisely as we can. So for example, the loop condition is just b. And this statement says if y was less than or equal than 2 before we subtract 1, then it remains so. Otherwise, it's non-deterministic. We build a model. And now in this model, is 5 reachable from 1?
No, really.
Maybe losing some people, but from 1, there's no path to 5. It should be easy to see. And so we know what we've just proven is that the error is, in fact, unreachable, and we have an abstract proof of that. Okay? So this is the CEGAR approach. I will say it's an over-approximation-driven, because a lot of the reasoning is sort of to build the right over-approximation, then do reachability over it, and then conclude that the program is safe, or there is a counterexample. OK. So here's another approach, which we'll call under-approximation-driven. An instance of it is impact or lazy abstraction with interpolants. And this is how it works. Instead of spending any time in generating this abstract model or abstract counterexamples, it says, generate just arbitrary paths to errors from a control flow graph. Once you have a bunch of these paths, check whether they're feasible. You can do it using an SMT solver. If there's at least one feasible path, then you have a counterexample, you're done. If not, you try to explain in a uniform way why all of these paths are safe. And you can use interpolation or weakest precondition for that. Once you have this explanation of why this particular path that you picked is safe, you check whether this happens to be an inductive invariant. If it is, then you're done. You've just proven that the program is safe. If not, then there are some paths that you haven't looked at in your program that are safe for a different reason, or maybe unsafe for a different reason. So you go and pick more paths, check if they're feasible, and keep going on and on. Okay? So here the approach is under-approximation-driven in a sense that a lot of the reasoning is in this part, where you deal with a bunch of concrete executions, and you're trying to decide whether they're feasible or not, or generalize things from them. So let's see how it works on exactly the same program as before. I haven't changed anything. Error is still unreachable. So what we're going to do is first we're going to pick a path. Any path through a control flow graph will do. We can pick this one that goes 1, 2, 4, 5. We then check whether this path is feasible. Of course, isn't. And then we get a proof why it is infeasible. And the proof here is written as annotations, which basically say that each annotation represents a set of reachable states from the top. It's an over-approximation of that. And each pair of annotations together with an edge form a Hoare triple. So you have to substitute the edge with an appropriate action, and then it will form a Hoare triple. So here we'll see this proof tells us that 5 is unreachable. The over-approximation of reachable states is false. Okay. Now, this proof is not yet inductive because we have this location 2. The loop had 2, and we haven't seen it twice yet. So we're going to look for another path, maybe the one that goes through the loop once and gets out of the loop, and then gets out and goes into an error. We check whether this path is feasible. It isn't. Right? How do we know it's not feasible? Well, the program is safe. We already know that. So they cannot be feasible counterexamples. And so we use, for example, interpolations to generate a proof that explains why this counterexample is infeasible. And we get something like this that says, so initially we start with everything, then y is less than 2. We subtract 1, y is less than 2. We go into a loop. We try to get out. We can't. So there's nothing reachable at 4 in this case, and nothing is reachable at 5. So now we also see that the annotation here for 2 is subsumed by the annotation here at 2. So we, in fact, have an inductive proof of safety. Right? If you look a little bit through this sort of Hoare annotations, you can now generate, apply Hoare rule for loops and get using the inductive invariant y less than or equal than 2. So that's an example of an under-approximation-driven approach. Yeah.
Confusion. So if it's an under-approximation, then you don't explore these infeasible paths, right? You're doing something else here.
Again?
If it's an under-approximation, if you're just exploring under-approximations.
So I pick a bunch of possible executions through a control flow graph without using any abstraction or anything. No, I don't know that they're feasible or not.
So why do you call it under-approximation?
Because I deal with concrete executions. So I actually write the formulas that represent the exact executions. And then I check if the formula is false, and I've represented no executions. And if the formula is something else, then I represented some executions. So I deal with concrete executions. If I find a counterexample, it's a concrete counterexample. But I deal with this symbolically. And so in this case, I can write a symbolic expression that represents what seems to me many executions, but really it represents nothing. But the meaning of it is what it represents. The meaning is the under-approximation with respect to the program.
Right, it's just a thing. I mean, you cannot have a concrete execution going from 1 to 5, right? It's just a symbolic execution, and, which is infeasible. So
Well,
yeah.
we can debate the terminology. So you could say that I'm working on this unrollings of a control flow graph, and the unrolling somehow over-approximate what the program does. And I'm thinking I'm working on the concrete executions, and I'm just using symbolic techniques to represent them. And it's just really a terminology difference. But if you want to allow that step for me, then I can't say that, well, there's over and under, and we combine the two. Just the story doesn't work as nice. OK, so when I'm going to show you the techniques that we have, I'm going to show it at a much higher level than the example that you saw. And so I want to show you the things that you saw, but at a higher level, where we don't look at the details, but we just look at how the exploration happens, where the over-approximating part is and where the under-approximating part is. So we're going to look at the skeleton of a program. And I'm going to show you the over-approximating approach here in sort of high-level pictures, and then an under-approximating approach here in other pictures. And that should make sense in the next slide. So this is what happens with an over-approximating approach. We go through this explore, refine, explore phases, where we build a model. We then refine the counterexample. We build more models. And the explore phase will look like this. We start with a control flow graph node. And initially, it's labeled by whatever the initial condition is. So blue means it's labeled by some formula over the predicates. We then make a step. So we find a successor, or pick a successor. Successor is not yet labeled. We just picked it. We then compute the abstract transformer. So we get the label for that successor, again, over our predicates. And we keep doing so. We pick a successor. We label it until we find a successor that corresponds to an error location, in which case we'll say, OK, we have a counterexample, this one. We have to go through refinement. So we have to analyze it, see if it's infeasible. And if it is, get new predicates. And after we go through the refinement step, we go back to the very beginning. We don't always have to go to the very top, but it's simple if we go to the very beginning. We now have more predicates, and we repeat our exploration. Again, we start at 1. We go to 2. We label 2. We go to error. And if our refinement was good enough, then this time an error becomes unreachable. That means we label it with something, but the something will be false. We'll then go find another successor of 2. So here it's in a loop, so 2 is a successor of itself. And then we check whether the annotation here is subsumed by the annotation here, whether we've seen all the reachable states. If so, we terminate. If not, we keep exploring until we get new error, new refinement, and so on and so on. That's sort of clear? Now, in the under-approximating approach, we'll also have exactly the same steps, the explore, the refine, explore, except what they do is slightly different. The explore step just picks a path through a control flow graph. Right? We haven't labeled it. We don't know whether it's feasible or not. We just picked a path, so everything is labeled by gray. We then check whether it's feasible, and if it's not, we use interpolants in order to get a proof or compute an over-approximation of reachable states along this path. So I'll use orange color to indicate that we have labels. They're also formulas over program variables, but they come from interpolants. And of course, if this path is infeasible, the error state will be labeled by false. Then we pick another path, label that path, and keep going on like this until, again, as in here, we'll get that something at the bottom is covered by something at the top. Something at the bottom has a label that's subsumed by something at the top.
So initially, these things don't really look very different because at the beginning of something like SLAM, you only have a control flow graph, and all the model checker is doing is exactly picking just the path arbitrarily to error, right?
Yes.
Because initially, the abstract transformer is just the identity, right?
Yes, absolutely.
Right.
So the two things are really, really similar, and I'm trying to argue that they're very, very similar, and they should be combined. I'm going to show you how, exactly for these reasons. The differences from what you mentioned, for example, is what do you do after? In the under-approximating-based approach, you take the proof and you extract labels from the proof. In the predicate abstraction approach, you don't do this. You take the proof and you extract predicates from the proof. You forget the actual proof that you had. And then you go back to your over-approximating step and see whether these new predicates are good enough to rule out the same problem happening again.
So here's a puzzle. So what that means is that the over-approximating technique actually computes stronger predicates than the under-approximating technique.
Mm-hmm.
I mean,
it could be.
Yeah, I mean, because if you take the interpolants, all right, and you extract predicates, and then you run predicate abstraction will compute something at least as strong as those interpolants. Your blue labels will be at least as strong as your orange labels.
Right, modulo various heuristics. But if you take the strongest predicate
assuming you take the most didactic version of predicate abstraction that says, compute the strongest Boolean combination, compute the best postcondition using the predicates, right? In fact, if it doesn't compute something as strong, you're probably in trouble.
Absolutely.
Right? So really, the over-approximating technique, the blue labels are actually stronger than the orange labels.
Yes. Because the orange labels are only good enough to rule out those counterexamples, whereas the blue ones may be good enough to rule out future counterexamples that look in a similar way.
So maybe about under-approximation, right? In other words, those interpolants that you're computing come from under-approximations of the program's behavior because they come from just partial behaviors of the program. And yet, they're really neither under-approximations nor over-approximations, are they?
The labels themselves?
The orange labels are neither under-approximations.
At the heart, both are using generally just traces, infeasible traces, right?
So
to get their
in principle, so the orange labels come bottom up. You generalize something, right? You have something very concrete and you generalize them into those labels. Whereas here you sort of come top down.
Well, okay, let me think of it this way. Now, is BLAST an over-approximating or an under-approximating?
So can you hold this on for a second? So I'm going to get to a picture of our approach, and then I can show you how you get all these points in the spectrum by specializing just various parts in this algorithm. Then I can show you exactly where a BLAST fits in into this picture. Okay. So I think I'm quite close to that part. So the first thing, so this is maybe sort of the discussion we just had to some extent. So if we look at these two techniques, we can try and put them into the space. And this is an ideal picture. They don't necessarily look like this. We have this number of refinements here and cost of exploration, cost of building the labels. In an over-approximation-driven approach, the cost of exploration is high. We put a lot of effort in computing the predicate abstraction. In under-approximation-driven method, the cost of exploration is very low, but the number of refinements can be very high. because we don't compute labels which are strong. So we sort of have this two parts where one has maybe few number of refinements but very expensive cost of exploration. So if you get the right predicates then and you're lucky, you terminate with a few iterations. And here you may need a lot of refinements to combat the fact that your labels are too weak. Okay? This doesn't reflect performance. It's not the case that, for example, fewer refinements means that you're faster. Right? So it's not clear how this affects performance, but what we'd like to have is an algorithm that can be in between these two. Not necessarily an algorithm that at any point, but an algorithm which is easy to control, maybe dynamically at runtime, to switch between doing more of this or more of this. And this is what this work is. So this is UFO. This is a picture that you should all be familiar with because this is an infamous state space explosion, which is a big problem in model checking at least. And the UFO algorithm sort of has this note. On one hand, it's an interpolation-based under-approximation-driven algorithm. It uses orange labels. And on one hand, it's a predicate abstraction-based algorithm that uses blue labels. And what we have on top of it, on top of this algorithm, one of the things that sort of makes it work is we have a novel interpolation-based refinement that makes this whole thing work together. So what I'm going to talk about next is I'm going to show you the algorithm at a high level. And I think then I'll just concentrate and talk more about the refinement part. So this is how UFO looks like in a nutshell. So this is exactly the same picture as you saw before with blue labels and orange labels. And what I'm trying to convey to you is that we'll combine things. So what you should see is one picture that has both blue labels and orange labels. If you see that, then that means we've combined something. It's going to use exactly the same steps as before. There's going to be explore, refine, explore. So let's go. So first we start in exactly the same way as predicate abstraction. And so we find some location L, we label it, we then go and see what the successors are. L happens to have two successors, an error successor and some inner one. We pick another, the inner successor. We keep going on, expanding and expanding, and then we hit L again. So L is a loop head of something. We find the successor of L is also this error location. We check whether we've seen all the reachable states. If so, we go and compute the label for the error location. And now we have a possible counterexample. Okay? So now we're going to go to the refinement phase. So far, it was exactly like predicate abstraction. Now the refinement phase will be different. What we'll do in the refinement phase is we'll take this whole directed acyclic graph, and we're going to prove absence of counterexamples in it. Not one pass at a time, but the whole graph at once. And from this whole graph at once, we're going to get a proof that explains why there are no counterexamples in this graph. Again, all at once. And this is going to give us the orange labels. Now, what can happen here? So the orange labels will be, in some sense, strengthening of the blue labels. Why strengthening? Because, well, here error was reachable, here it's not, so it got stronger. But it's not necessarily uniform strengthening. It's not uniform in the sense that here the set of reachable states at this location can now be bigger than the set of reachable states at this location. So what we're going to do now for the next exploration phase, we're going to find out all of the back edges which are broken, which are no longer inductive. And then we can restart exploration from that point on, possibly with a new predicate that we found. Okay, that's it. So let's see how do we get the other algorithms. So say we want to get an under-approximation-driven algorithm. Then what we would do, we would say here, whenever you compute the blue labels, always use the most imprecise post you can. Use 0 predicates, always. So if you always use 0 predicates, here you'll just unroll every loop once. You then get interpolants to rule things out and see if you've converged. If you haven't converged, you unroll every loop once again. Check now if this bigger graph has a counterexample. If it doesn't, build the labels that it doesn't. Check that it is inductive and keep going on and on. Now, say we want the other way. Say we want to get BLAST or something similar to just the predicate abstraction algorithm. Well, we're going to use all the predicates we can. Every time we do more proofs or more interpolants, we're going to extract the predicates and use them in the next iteration. But also, why should we start the exploration from this point? We can start exploration from any point here or any point above it. So in fact, whenever we go after refinement, after we've proven absence of a counterexample, I've gotten this orange labels, we can then restart exploration always from the top, right? Effectively killing the orange labels, just using the predicates from it. And that will be a predicate abstraction-based algorithm. So how do we control this interplay between over and under approximating driven? Well, if we want it to be more under-approximating driven, then we throw away some of the predicates. We find out which predicates we don't want, throw them out. The more we throw, the more under-approximating driven we become, because more imprecise our post becomes. And if we want it to be more over-approximating driven, then the higher up in our tree we start. Higher up in the tree we restart. So that's our two numbers. So did that answer your question about where BLAST is?
I'll ask my question again later. It doesn't really relate to.
So you asked me where BLAST is and how it fits into it. So the way.
Okay, well, if you took a sort of very didactic version of BLAST, right, what BLAST would say is, well, when you get a bad path, right, then you are going to do predicate abstraction along that path to update the labels, right? So the extreme version of BLAST is the extreme lazy, right, where you're saying do predicate abstraction along the path, but don't propagate those predicates along other paths, right? Do the refinement very locally. So that would be the extreme lazy version of BLAST, which you wouldn't want to use necessarily, right? But if you think about that, that version of BLAST, right, is actually sort of a special case of impact, right? Because all it's saying is, I'm going to get the interpolants by, instead of taking them directly out of my SMT solver, I will get the predicates out of the SMT solver, and I will do predicate abstraction along that path. And that will give me a stronger
So this is like starting higher up.
And that will give me a stronger set of interpolants, exactly. So what I'm saying is then BLAST an over-approximation technique or an under-approximation technique? Because I would think of it as a special case of impact in the extreme.
So I would say it's an over-approximation-driven technique, because the main engine for reasoning is the post-computation of predicate abstraction.
Yeah, okay.
So you do a lot of things so that then you can apply the abstract post. And
in the end, isn't it just computing an interpolant for a path?
Well, it's computing a set of reachable states. It's not really what it is computing, because at the end of the day, anything that you compute would be an interpolant for this problem, right? It's a question of, to me, it's a question of how it is computing it. Is it computing it by looking at executions and extracting and generalizing a proof, or whether it's computing it by doing something else?
Isn't that sequence of computations of postconditions, isn't that a proof?
Of course, at the end of the day, what it computes is a proof, right? So this would be.
Is that not an interpolant from a proof?
Yeah. I always thought of the distinction as just, do you take your abstract post and iterate it to an abstract fixed point, thus computing an entire over-approximation. And so the blue closed thing is that, right?
Yes.
Right, yeah.
Now, eventually, some other technique might do that, but I think to me, the over-approximation generally means not just computing the abstract post via predicate abstraction, but iterating to a fixed point.
Well, yeah, but ultimately we get a fixed point from all of these techniques.
Yes, but it's a question if you're doing that evenly.
Far enough.
So is BLAST predicate abstraction or not?
Well, if you move far away from this, then you'd say all of the things all that they're doing, they compute a proof, a Hoare-style proof of correctness of the program. Right? No matter which way you do it.
In the first iteration of predicate abstraction, do you have an under-approximation or an over-approximation?
It's an over.
As Tom said, you iterate a post, and so you
Under-approximation because you've looked at only at a subset of the control class.
so I want
No. Bebop does a full reachable fixed point on the entire control.
Yeah, but let's say that you're doing predicate abstraction. So you just leave aside Bebop. Just think about doing abstract interpretation in general, right? And you think about you're iterating that abstract post, right? After 2 steps of the abstract post, do you have an under-approximation or an over-approximation?
So that's what I don't want to. That's a discussion that I was trying to prevent in the beginning, and I didn't succeed. So when you look at those techniques, right, and you stop a technique at any point, and you say, I have an object in the middle of this technique. What is this object? And the safest thing you could say is that this object is a partial model of some kind. Could be an over-approximation, an under-approximation of some. It's a partial model. It describes some information that you have so far.
Some information about some subset of the behaviors.
It is.
So therefore, it's both an over-approximation and
It is.
If it's bounded, right? If it's bounded, it's under, but it could be with respect to an abstract post, which is
over-approximations nor under-approximations.
Absolutely. So, but what I'm trying to promote here is the stresses on the keyword driven. So I'm saying some techniques are driven by their over-approximating way of thinking, and some techniques are driven by the under-approximating way of thinking. If you pick any of these techniques and stop it in the middle, then of course what it has is a partial model, which is neither an over-approximation nor an under-approximation. But if you look the way I was, well, maybe I won't go back just now, but the way I was presenting the 2 approaches, the CEGAR approach and the under-approximating-driven approach, then I would claim that what makes it driven is what is sort of the most computationally intensive box. Or do other boxes work towards the sum box, or they just work on their own?
But I could explain this another way, and I could just say, well, you're either computing stronger interpolants or weaker interpolants. Right? You're computing stronger interpolants if you use more predicates, and you're computing weaker interpolants if you use fewer predicates. Right? So you're just dialing the knob between strong and weak interpolation. And
but
as you go to stronger,
solving the fixed point problem.
But you're solving the fixed point problem in every case.
Well, no, the blue part I run until I get the fixed point. And then the orange part I just run on a bounded problem that I've generated through the blue problem.
Yeah,
so it's not as...
Yeah, right, okay, so that's, right, okay, there you're right. That's something else, because there you're saying that...
So the blue box
right.
generates an inductive invariant that's maybe not safe. The orange one generates a safe set of reachable states that may not be inductive. Right? And so, so that's the interplay. In one case, you say what's important. In abstract interpretation, you say what's important is to generate a set of inductive, an inductive invariant. Whether it's safe or not, that's secondary. So you prove your widening terminates. You don't prove that your widening is safe. Whereas in an under-approximating-driven approach, you sort of say, I want to prove why this bounded version of a program is safe. And then I hope that this will become inductive. So that's a...
That makes sense, and that is a difference. I'm not sure I understand why one is over-approximating and one is under-approximating, but it is a difference. Right? And one is more eager than the other. Right? The one that's going to a fixed point. Yeah, and that's definitely right. That there are cases where that's what you want to do, and you want to have some kind of abstraction where you go to a fixed point.
So again, the terminology is sort of something that made sense to us. And it also made sense to us because it sort of seemed like it makes a nice story where you have over and under and they come from 2 sides and you combine them. But perhaps that's a bad terminology and something else could be more effective at it.
So can I think of one on the left is really guided by proof search, the other one is really guided by counterexample search, and then some generalization of that. So the one on the left is really looking for a proof.
But it's a proof over approximation. The one on the left never looks at the actual program. It looks at sort of an abstract post, right. What your predicates.
So the proof can be over abstractions, whereas the one on the right is really looking for counterexamples for which you have to do concrete execution.
Yeah, but I mean, you could also think of the difference as being, essentially lazy versus eager deduction. Right, where you're saying, I'm being more eager when I'm taking a given set of rules and I'm going to a fixed point with this. It's like saturation proof. the points taken.
Okay, so here's the algorithm, if you really want to know. I don't really expect anybody to read it, but if you want, you can. Just wanted to point out that there's this explore part, which is the function that expands the control flow graph. And there's a refine part, which is this one line, and that's a sort of more interesting part from my end. So that's the one I'll talk about most of the rest of the talk. So just for the explorer part, whenever I show the slides, people often ask a question like, why do you go to an error state first, or what's the heuristic of unrolling the control flow graph? And what we've decided to do is to use the weak topological ordering. And is there anybody here who doesn't know what that is? Oh, okay. So a weak topological ordering is a topological ordering of the nodes of the graph that also indicates roughly where each loop starts and ends. So for this graph, this is the weak topological ordering. It's described as a sequence of nodes together with brackets that indicate such that the first element in the bracket is the loop head, and then the closing bracket tells you where this loop terminates. Okay? The reason why this is an interesting way to look at this problem is that if you want to compute a set of reachable states or apply abstract interpretation, instead of using a work list, you could do it in a deterministic fashion where you go in topological order, iterating each loop, each inner loop, until it converges before going to the next one. So here, for example, the exploration would be you go 1, 2, 3, 4, iterate 4 until it converges, then you go 5, 6, and again 2 until this converges, and then you go 1, 7, and so on. So you would end up doing all the inner loops before you do an outer loop.
So this would be classic in data flow with reducible graphs and natural loop identification.
Yes. But in abstract interpretation, it has this name, weak topological ordering, and whereas the difference is that it will also apply if you don't have reducible graphs.
Really?
So you could order a graph in the weak topological ordering. And the reason why we picked this is because it gives a deterministic exploration, so it makes managing things in algorithm a lot easier. But it doesn't have to be the best exploration strategy. OK, so if you don't have any more questions, then we'll go to refinement. So refinement, in our case, is based on Craig interpolation. That's a picture of Craig, if you haven't seen him before. So the Craig interpolation theorem basically says that if you have two formulas A and B, such that A and B is unsatisfiable, then there exists an interpolant I that's implied by A and is unsatisfiable together with B. Right? And this is one way to write it. In sort of model checking applications, we typically think about A and B being unsatisfiable. In the original theorem, it was A implies B, and you want to find something in the middle, I, so that you can apply the transitivity rule. We know that we can build Craig interpolant effectively from resolution proof of unsatisfiability. And it's well known that we can use it for over-approximate set of finitely reachable states. So let's see how it's used in model checking. So I'm just going to show you an example of how it is used to over-approximate reachable states, and I'll get to show how we use it. So if we write Ri for the I step of the transition system, and then we take as an A part of our interpolant the set of initial states and R at the 0 time step up to R to n steps, and we'll take B as a set of bad steps. If A and B is unsatisfiable, that means there is no bad execution with n plus 1 steps. And then the interpolant is an over-approximation of reachable steps and of states reachable in n steps that does not contain any bad states. Right, is that sort of clear? Just from the definition of the interpolant, it will be only over the variables which are common to the bad states and the last step, and it will be an over-approximation of A, so it will over-approximate the set of reachable states. So this is the picture. So A is the set of reachable states. The interpolant is an over-approximation of it that's inconsistent with B. Now, what we're actually using here is not, this is just how you would do an interpolation to find out a set of reachable states. What we want to do is, given a path in a program, build a Hoare-style proof that this path is infeasible. So we'll need more than one interpolant. And there's a concept called interpolation sequence or path interpolation that does this. And it says something like this. Given a sequence of formulas, AI, such that the conjunction of these formulas is unsatisfiable, an interpolation sequence is a sequence of formulas I1 to in minus 1, such that each I is an interpolant of the corresponding prefix and the suffix. And then if I pick any interpolant that represents a prefix up to k, and I take the k plus 1 step of my transition system, then I'm going to imply the next step, the next interpolant in the sequence. Okay? So that's basically the Hoare rule of the Hoare proof rule. It says this is the precondition, and I do this step, I get into a postcondition. So pictorially, this is how it looks like. We have this formulas A0 to A6 that represent transition relations. We're going to get our interpolants, which will be I0 to I5. Each one represents the prefix, over-approximates the prefix. And then we want to know that the A0 implies I0. And we want to know that A1 and I0 implies I1. And A2 and I1 implies I2. And so on and so on and so on. Okay? So if AI is a transition relation of step I, then the interpolant sequence will be a Hoare-style proof of safety of that trace. And this is the principle that, for example, is used by Impact in order to build annotation of its tree unrolling. Questions? You seem like you're thinking about something, so I don't know if you have a question. Or,
I'm not thinking about that. I'm thinking about something else. I'm sorry.
Okay.
I'll try to pay more attention.
Maybe I said something that was not quite.
Sorry.
So this is the part where that gets to be an interesting part. So using path interpolation, we can get rid of a single path. But we have a DAG. And so we want to get rid of all of the paths in the DAG at once. And to do this, we introduce this new concept that we call a DAG interpolation, as opposed to path interpolation. And this is what it is. So what's an input to the problem is, so the input to the problem is this graph, the DAG graph, together with each edge being annotated by a formula in such a way that along any path, a conjunction of the path formulas is unsatisfiable. And then for what we want to get as an outcome is this interpolants I that label each node of the DAG with a formula and that satisfies the following two conditions. First, if you pick any place, like say this one, then this formula will be an interpolant of any prefix to it and any suffix from it. Okay? So for example, here I2 has a single prefix but has multiple suffixes, and I2 has to be an interpolant for each of the suffixes. And the second thing that we want is that if we pick the formula, say this one, I2, and pick any formula of any edge, then they together should imply the interpolant of the next node. Okay? So here's an example that for I2 has to be an interpolant of pi1 and pi8 because of the paths 1 to 7. And it also has to be an interpolant of pi1 and 2, 3, 6, and 7 because of that path, and so on. And we also want this local rule to be true, that for that an interpolant together with a formula of an outgoing edge implies an interpolant at the next node.
So I1 is true and I7 is false.
And I1 can be true and I7 can be false, yes.
But
if
so far, right?
Yes.
They're not variables.
Yes. That's true. Okay. So the question is, how do you compute this thing? How do you compute a DAG interpolant? So you could try and maybe break the DAG into a tree, and then try and compute an interpolant at every path, and then maybe conjoin interpolants that came from nodes that were joined in a DAG, or something like this. But that would not be efficient because this would be linear in the number of paths through the DUG, which will be exponential in the DUG. So you somehow want to solve this problem in an efficient way. By efficient, I mean at least linear in the size of that DUG. And this is what we propose. What we actually do is sort of not quite a happy end for us, because we reduce the DUG interpolation problem to a sequence interpolation problem with the step that I'll talk about, this clean step. That actually ends up being quite expensive. And this is something we're still working on, trying to figure out, is there a better way to do this? But let me first explain to you what's actually happening here. So the way we reduce it to a sequence interpolation problem is through the following steps. First, we encode this whole program, the graph and the annotations on edges, by a sequence of formulas A0, AN. I'll show you how this is done in such a way that every satisfying assignment to these formulas corresponds to a satisfying assignment through the graph. We then get the sequence interpolants of these formulas. So I1, for example, is an interpolant between A0 and the rest, and I2 is an interpolant between A0, A1, and the rest. And then this gives us almost what we want. Well, I'll show you that this also includes some of the variables which we don't like to be in our interpolants. And we go through this clean process that gets rid of those variables. Okay, so let me show you a step-by-step picture of it. So the encode process is really simple. This is what, if you think about this problem for a minute, this is probably the first thing that you're going to come up with. The idea is to introduce Boolean variables, one Boolean variable for each node in the graph, use the Boolean variables to encode the structure of the graph, and then add constraints saying that if you've taken an edge, then the condition on this edge has to be true. So if you look, this is sort of what this looks like. It says initially v1 has to be true because we start at 1. And then if 1 is true, then 2 has to be true, and the condition has to be true. And if I'm at 2, here I have 2 successors. So either I go to 3, and then pi2 has to be true, or I go to 7, and pi8 has to be true. Right? Because when I go to 7, pi8 is true. Okay. But what I'm also going to do is I'm going to do this encoding, and I'm going to order it in a topological order according to the topological order of the nodes of the graph. The topological order simply means that whenever I'm at the node, I've seen all of its predecessors already. Okay. So now I'm going to take sequence interpolants between this point, this point, this point, this point, and this point. Okay. So just to show you what this means, I'm going to do an example of one interpolant in a sequence and try and explain what this formula actually has. So say we're going to pick this position, A3. Right? So say we're going to get I4, which is whatever the fourth element in our sequence. So if we cut these constraints here, what happens? So if you think visually what is being represented, well, the constraints up here describe this part of the DUG. Right? They have all the paths together with all of the edge labels. And the conditions which are left are these things. Right? So effectively, by drawing a line in constraints here, it's like taking a DUG, finding a node in it, and then cutting it in such a way that everything which is topologically under it, so either reachable from it or incomparable to it, goes at the bottom. Everything else goes to the top. And of course, there are some edges that cross this boundary. Cross this boundary means that in this edge, I'm using a variable, say, v7. And I'm using the variable v7 here as well. So what I'm interested in is I want to get a label of 4. But what will the interpolant be? Well, the interpolant will be an over-approximation of this formula that's inconsistent with this formula on the common variables that described using common variables. So it will actually be an over-approximation of all of those guys. Right? It will be the set of reachable states at 4, at 5, and at 7 that over-approximate what you could get at 7 from here, at 3 from here, and at 4 from here, and at 5 from here. Okay? And this is the variables we want to somehow get rid of. And this is our clean step, getting rid of these variables. And it's very ugly, and it's very expensive. So instead of looking at the formula, let me try and explain what that means. So if you look at this formulas here, what you get, how does the interpolant look like? Well, ideally, it will look like a clean formula that will say V7 is true and some constraint about V7, or V4 is true and some constraint about V4, or V5 is true and some constraint about V5. Right? And if a formula would have been in a nice clean form like that, you would just throw away the 7 and 5 parts, and you just keep the 4 part. Okay? But that's fairly easy to do even if a formula is in a strange state, because we can just substitute true for V4, false for V7 and V5 and simplify the formula. But another part that we're going to get is that any variable that say only in scope at this location, according to interpolation, could appear in here. And it does. And it often appears inside here in the form of some tautology. It can't appear there in any meaningful way, because this has to over-approximate the set of states reachable here. This variable is not a scope. It cannot be constrained. But it can appear in tautologies and in various strange ways like this. And the only way to get rid of it that is actually sound is to universally quantify it out. Okay, and this is what this clean step is. It says substitute some variables by true, and then sometimes we substitute some variables by false, and then whatever you cannot get rid of, quantify things out. And this is where the big bottleneck of this procedure is, because even so we can apply various heuristics to try and find tautologies and get rid of them in a better way than by just giving it to quantifier elimination procedure. At the end of the day, that's what we do. We go to the 3 and we ask it to quantify whatever is left out. And in practice, if the algorithm ever gets to this point, that's more or less means we lost. So if we ever need to go to the 3 and ask for, do a quantifier elimination problem, and the problem is not very, very quick, then this typically means it will become gradually really, really slow in this iteration and the next one, and then we will not converge. Okay, so just to summarize this whole procedure. So we start with a DAG, where edges are labeled by formulas. We encode the DAG. Encode the DAG in using these extra variables. We use sequence, interpolating sequence in order to get the initial guess of the labels, and then we use quantifier elimination to make the labels what we want. So we use a single call to an SMT solver to do the refinement. But we do have the quantifier elimination step. And in principle, so I know how to phrase it. So we have a technique now that doesn't use quantifier elimination but requires more SMT calls. And in principle, one can prove that you don't need the additional SMT calls. That is, all of the information that you need is in the initial proof. But in order to do this, you need to sort of open the interpolating procedure and start dealing with it. That is, change the interpolating procedure itself. Whereas so far we've been using MassSat as a black box, sort of fitting things into it and then extracting them and massaging them ourselves. So this is UFO in a nutshell. We start with blue labels, we mix orange labels, we continue with blue labels. We have blue and orange labels. How many orange labels you have? You one, we call under-approximation-driven. How many blue labels you have? That's another we call over-approximation-driven. And you control the algorithm by having more or less of those labels.
Can you say a little bit about, are you going to say something about the heuristics you use for making those decisions?
Right now, we don't put a lot of effort into it. So right now, the heuristic that we use is we use orange everywhere and then blue at the lips.
And when you compute the predicate.
So we do exactly this.
Well, so you were saying that you have some knob that you can
So the
turn,
choice
right?
is you could say don't restart exploration not from the last place you left off that got broken, but restart it from other places.
Right.
And we haven't tried that. We always restart exploration from the very bottom.
To the bottom, yeah. But so when you use predicates to compute your blue labels here, how do you decide which predicates you actually want to use?
We use all predicates from the predicate abstraction. But then we often use Boolean predicate abstraction. not Boolean, Cartesian predicate abstraction as opposed to Boolean. So something that's inexpensive to compute. But we've really been concentrating not on this heuristics yet, but extending this further into other abstract domains. I'll mention a little bit about that. So what I've told you is about UFO sort of as an algorithm. But there's also another story of this, which is UFO as a framework. So this whole thing is built on top of LLVM as a front end. It's publicly available, including source code. So we'd like people who are interested in this maybe who are interested in different heuristics to try them out and help us. In terms of the architecture, it's fairly straightforward. We start with LLVM front end. We use LLVM optimizer in order to massage the program to make it simpler for verification. So for example, we don't deal with memory at all. We only deal with integer programs. But LLVM optimizer does pretty good job at inlining lots of things. So not just inlining functions, but also inlining memory accesses into registers whenever it can. And then we build the cut point graph. So it wasn't apparent here, but we always work at a representation of a program where a single edge is the longest loop-free path instead of just a single statement. And we call this a cut point graph. That's a control flow graph representation. And then we build the abstract reachability graph. And while this is happening, you can pick a refinement strategy, which is several ways to use this DAG interpolation procedure. You get to pick what abstract post you want. And we support predicate abstraction, but also now some of the abstract interpretation domains. And then the expansion strategy, which is how far back and forth you want to go. And we use these three and massat together. We use these three mostly for satisfiability and for simplifying the problem. And then when the problem is simple enough, we use massat to generate the interpolants.
What does it mean to simplify the problem?
To extract an unset core.
Oh, okay.
So we found out that as the problems get larger, using massat to directly extract interpolants is just not feasible. So what we do is we add lots of assumptions, do check with assumptions, minimize, build the minimal unsatisfiable subset, and then take that part and give it to massat to get the interpolants.
Do you try to so we don't necessarily give the minimal unset core?
So what we actually do right now, we have several heuristics being implemented which we don't use, but what we actually do right now is we do it 3 times. So we say, you put assumptions everywhere, check with assumptions, then it comes back and removes the assumptions which became false. Remove the subformulas that became false, and do this again, and do it 3 times, and then.
Do you remember anything about how much more you get by doing it 3 times instead of?
No, but I can give you the numbers. I don't remember offhand. Sort of, I was trying. You should really talk to him. So you tried a few numbers, and then 3 stayed. Okay, so I just want to show you some numbers just to show whether these things work or not. And sort of the takeaway point is that combining things are good, but we don't have a silver bullet. So we don't know how to combine things that always works. And so what I'm going to show you is experimental results for the following configurations. We have something which we call UD, which means you never have blue labels. You always use post that's true, most imprecise one. We have OD, which means you always restart from the very top. So you compute the orange labels, and then you just take the predicates and restart from the very top. And you either use Cartesian predicate abstraction or Boolean predicate abstraction. And again, the abstraction is always over a loop-free program statement. So even the process of generating a predicate abstraction is quite expensive. It's not a single simple statement. And then the 2 combined one, UFO combined with Cartesian and with Boolean. We've used, what we validated this on is the software competition benchmarks from last year. We didn't compete because this work was done for TACAS, and so the deadline for the work and the competition was at the same time. And we didn't make it. We also have some of the pacemaker benchmarks that ours worked on before. And we've compared it just to sort of compare it with an existing tool. The only one we've compared it against is Wolverine. But since then, we looked at, for example, what CPA Checker is doing, which is the winner of the competition. and we do quite well compared to it. So here's the total numbers, and they're not very meaningful, but people often like to see like what happens in total. So you have that the Cartesian predicate abstraction seems to be the best, as in it takes less time and it solves more instances. But the benchmark is very uneven, so it's very hard to sort of look at the global number and know what's a good technique or not. So if we go deeper and look at some of the examples, and if you've probably seen these examples before, either in a competition or from prior work. So this is a token ring protocol, and this is the SSH server examples from BLAST that Sagar has done a while back that encode various handshaking protocol verification parts. And so here we get that as promised, as you go down the predicate abstraction part, the number of refinement goes down. So the more predicate abstraction you do, the less refinements you have. Doesn't mean that your time gets smaller, but at least we have that. And then in terms of time, it's sort of a little bit all over the place. So sometimes, like here, it's good to not do any predicate abstraction, because predicate abstraction just takes too long, and so you die in the first few iterations. And sometimes it's really, really good. Sometimes you just get the right predicates, and you terminate very, very quickly. Whereas simply unrolling things and hoping that the interpolants will converge doesn't work.
In those experiments, did you use force covering for UFO?
No, we haven't used force covering at all.
It's tricky when you have
Yeah, okay. I'm not sure exactly how you would apply it. But just
The force covering.
Let's say,
The force covering is a heuristic that would say, if I have something that is not inductive, check whether it happens to be an inductive loop invariant on the side.
It's basically adding a little bit of eager deduction into impact, and it's for the path-based impact. It's very important, but it's not. I don't really understand, whether it makes sense.
Right. So our sort of intuition was the predicate abstraction step would do this for us. Right, that it will generate strong invariants.
Right, I'm just asking for the one without predicate abstraction.
Yes, but no.
Because usually, that's impact by itself is really too lazy. And if you wanted to get it to converge on loops, you have to be a little bit more eager. So.
Yeah. So no.
For reference.
Don't do that at all. And then this is a look at unsafe. So here, of course, sort of what you'd expect. Again, the number of refinements is the same. More refinements here, less here. But it's hard to see in this table because it doesn't solve a lot. But what you see here is that if you have unsafe examples for places where there is a counterexample, then unrolling is great, because you just unroll, give it to an SMT solver, and that's it. You don't waste any time building something that you know will not work. So the positive part is that we know that the snobs that we have are useful, that you could configure the system in such a way that it solves a particular example faster. The not so good news is that, or maybe it's good news for our future, that we don't have a silver bullet that says, do this configuration, so this is how you infer them from a problem, or any of those things. So this is more or less the observations. There's
In competition mode, would you switch between the...
If we find time, that would be. So what we find sort of the best strategy just by looking at the numbers, it seems that you should try a couple of iterations with just being very lazy, and then gradually bring predicate abstraction. Because that's the cases where you do really, really bad. If there is a very clear counterexample, which is at a very few iterations, then you're much better off just unrolling and finding it, and then spending time building your set of reachable states. So there's a lot of related work to this. So this just highlights some of the tools. So of course, Ken has this impact and impact 2 tools. There's a tool Wolverine by Georg Wassenbacher, and it implements an impact algorithm, but with bit level precision. We've compared to it, we do a lot better, but that doesn't mean anything, because we're not bit level precise. We use a different solver. So that doesn't tell you anything about the underlying techniques. And there's also a paper that came at VMKI this year called Ultimate, which is impact with large block encoding, which is in some sense very similar to an instance of our system, but they don't have the predicate abstraction part. And the refinement that they do is still based on each individual path, as opposed to a whole DAG. We've also looked into interprocedural version of this. So we have a tool called Whale at VMKI that would use interpolants, but in a slightly different way to try and get procedure summaries. We haven't yet combined the two together, but that's on our to-do list. And there are several small sort of technical issues because the interpolation problems that we solve are slightly different. But they should play well together. There's also a work coming up from Natasha Sharigina's group on, again, using summarization, using interpolation to get function summaries. Their goal is not really to try and prove programs, but rather to try and prove that two versions of the programs are equivalent to some extent. So they call it upgrade checking. It means that if you take an app program and you've changed some of its functions, you want to reuse the previous proof to prove that the new version, even with changes, is still safe. So the difference is that they don't look for the inductive generalization part. They only do a single interpolation problem. Of course, so this was in the beginning of the year. I think we've collected this list in the beginning of the year. And there's more recent work that's also related. So there is, in this year's CAV, there was a software model checking via IC3 by Cimati and Grigio. And it's really very similar to a large extent with what we do in the sense of reusing the orange labels. That's sort of the key intuition in there. I don't quite agree that they've extended IC3 to software, but at least they bring the orange labels and they also show it's quite effective. There's a work by Ken on duality, which is does the interprocedural version of this problem. And Nicola has generalized probability-directed reachability, which is sort of opens all of this up and says, at least one way I view it is that it says, let's not just get interpolants from a proof. Let's force the solver to work in such a way that we get the interpolants we want. And there's several other papers here, which are sort of, there's a space here because they're related, but maybe not as closely related. There's a work by Rybolchenko et al. On solving recursion-free Horn clauses. And this is really, really similar to the DAG interpolation problem we have. It's actually probably a generalization of it. But unfortunately, I've tried reading this paper. I don't understand it. If anybody here can explain it to me, that'd be great, because maybe they already solved all the problems. And then there's this whole other line of research, and I've put one paper here by Nishant, which comes from sort of program analysis perspective, but it's really solving the same problem. And in program analysis perspective, they would say, if I want to reason about a program with lots of functions, well, I can inline all of them, but that blows up. So I want to have some sort of strategy of how to inline function and maybe use the solver to guide me how to inline back and forth. And so they have a paper at CAV this year where they do propose a particular strategy that seems interesting, but they do it completely outside of the solver. So really from a program analysis perspective, you build bounded programs and then you feed them to the solver, and then the solver gives you results, and based on that you decide how to unroll the bounded program.
That sounds also very similar to what Shah's and company are doing. Is that the paper? Is that this reachability modular theories?
Nope. It's not that paper. That's another paper that could have been included in this list.
Okay.
Yes.
That's a very similar description.
Yes, so they have something that they call stratified inlining.
Yes.
Right, so that's that you first inline just using uninterpreted functions and based on satisfying assignments inline forward. The alternate part says that you don't have to start from main, start from close to your assertion, and then go out and then, and also use interpolants to learn summaries of functions that you've already seen and use those instead of the actual bodies, if you can. So if I'm missing something, let me know. I'm sure I'm missing a lot of more recent work. Okay, so if you're interested, so this is sort of towards the end. If you're interested in what UFO is, this is sort of the nutritional label. That's what you get in the box. There is some abstract interpretation now, which I haven't talked about. There is some verification condition encoding, some CEGAR loop, some interpolation. It's all mixed together. You apply it typically for 1 second, and it may work.
What's the unsaturated fat?
You make it, Jon. So check it out. Talk to us. Look at the papers. So just to conclude, so sort of our past, present, and future. So we started this work with this tool called Whale. Where really just were interested in extending interpolants to interprocedural analysis. We've built the tool. It worked OK, but we couldn't find lots of problems for it because there aren't that many problems with recursion that we could get our hands on. And so, but what we've invented in there is this concept of state transition interpolants, which is, I think, is still quite an interesting concept to explore further. And so we moved to some other domain. We said, OK, well, if we don't have recursive programs, we still had this dealing with DUGs and dealing with cut point graphs. And we said, well, let's look at the software competition benchmarks and what we can do with them. And this is where UFO came from. And after working on that and looking where predicate abstraction helps or doesn't help, we said, well, we should really bring abstract interpretation into this picture as well. And so now we have this new work that will appear in SAS. It's called VINTA. VINTA stands for, what does VINTA stand for?
Verification with interpolation and abstract interpretation.
And maybe Alice can at some point tell you more about it. I found out, it was a big surprise. So what VINTA is really, the meaning of VINTA that I knew, is a boat from the Philippines.
A what?
A boat.
A boat.
Okay, right. So you have a whale inside the ocean, the VINTA on top, and UFO. It's a colorful boat with like a sail. But this is not a logo. So apparently in Telugu, which is an Indian dialect, VINTA means novelty or surprise. So if you go to any translation and you say translate novelty into Telugu, you get this. This is their script. And so apparently that means VINTA. So what VINTA adds to the picture is using abstract interpretation, which means we need to figure out how widening fits into the picture. And we have an interesting story there. And also, it made our interpolation problem so much harder, just because the abstract interpretation would unroll the control flow graph much more. And it let us sort of rethink how we were using information. So if you look at here, we generate orange labels, and then blue labels and orange labels. We never mix the two labels together. And so that forced us to think about how to do this. And we have this new abstract interpretation guided way to do DUG interpolation, basically where we would take the inductive but not safe invariants and bring them into the interpolation problem, so that the interpolation is not give me the reason why this program is safe, but strengthen the inductive invariants that are not safe to be safe, but maybe you lose inductiveness. And that was a lot more effective in that space. And that's it.
You're lucky. Urban Dictionary didn't have much to read.
We're not lucky, be careful.
Okay, thanks.